Now we see about AVR CPU. Inside the CPU, how an instruction gets decoded, and how does the instruction perform the operations. So as you can see here, we have our instruction. So this is our instruction from our program memory. So you can see that we have our opcode followed by two operands. So the instructions are fetched and they reside in your instruction register and then are passed to the instruction decoder. So the instruction decoder then splits it up into the opcode, which is basically add and its operands. So the operands here are, your destination is your R17 and your source is R30. So the instruction decoder then sends the opcode to the ALU signal, control signal, and then the operands are then passed through the bus to your general purpose registers, because that's basically what your operands are. So once those addresses are sent to your general purpose input outputs, so now RD and RR are placed in your A and B ports of your ALU, and then your operand of add is supplied to the ALU. We have the resultant comes out and then again is passed over into the general purpose register and gets replaced with the old value of RD. And as you can see, in this case, every instruction is of 16 bits. Now we are also going to see another detailed view of the instruction flow. So here you can see that we have our assembly code, but this is kind of a pseudo assembly code. So the idea here is we have to take the value from this memory location, which is nothing but an input output, but referenced as a memory location. So we take the value from 17 and we need to bring it to A, and then what we need to do is then we also need to move the value of A to B. Then we will need to take the value which is in 6, which is this memory location 6, into A. So speaking, let's say if you have a value which is 9 here, so we would first move the value of 9 there and then move the value of 9 by the second instruction, and then what we will do is we need to move the value from here, which is 5, into A, which will be that. And then the fourth instruction says that we need to add them both together using the ALU, and then add 5 plus 9, and once we have 5 plus 9 would give you a value of 14, or E. So we move the value of E to the location A, and then we can see that we want to move this E to this memory location. So at the end we should actually get a value E in location 7. So that's basically a bird's eye view of what we are going to do, and now we're going to see how this is going to be executed by this particular processor. So just for the case of simplicity, we are using A, B, C, D, just 4 registers. Technically they could correspond to, R0, R1, dot, dot, whatever, R4, but just for the case of simplicity we're just using A, B, C, D. Okay, so to start with, what happens is, as you can see, that's our program counter. It puts the address it's going to fetch the instruction into the address bus, and it's going to inform the program memory that it wants to read. So now as you can see, the memory is fetched through the data bus and goes to the instruction decoder. So the value 31 typically means that it's basically LDI, say from memory location 17 to A. So once the instruction has been fetched, you can see the program memory gets incremented. So in other words, when it's actually a particular instruction is fetched, automatically the program counter increments. So now it is actually pointing to the next instruction the processor is going to execute or fetch. So as you said, basically the 31 is an instruction with an LDI with location 17. So here you can see it then splits up the value into the operand, which is 17, and the opcode, which is LDI. So now it places the value of the address 17 in the address bus. Again, it informs that it wants to read from whichever address that is. And as I said, let's assume that it has a value 9. Now the value of 9 will actually come through the data bus and will get the instruction will be executed. The execution is LDI, which is loading it to A. So now our processor puts the PC count, which is 1, into the address bus. Again, tells it I want to read from program memory, and then gets the next instruction into the instruction decoder. So now the instruction decoder will decode that instruction into its opcode and operands. So, and then you can see the program counter will increment to the next count value, which is 2. So now this one, the C4, basically the instruction tells that it needs to move the value of whatever is in A to the B register. So now we place our second the next program counter address into the address bus. Again, tell it you want to read to it, bring in your instruction, decode it, and then increment it, your program counter. You can see now program counter is 3. So now that particular instruction says that you want to fetch something from 6 and put it in A. So therefore it puts the value of 6 in the address bus, tells it wants to read, and then brings in the value whatever is pointing at 6 is at 6 address, which is 5, and now it's going to execute it, which is again an LDI instruction. So it's going to load it in A. So the next one, you can see we're going to use our next PC counter value, which is 3. It's going to get again that value from your program counter will be 81. It's going to actually decode that value. So now it's got an opcode and 2 operands. So therefore we can see that 81 is nothing but an add of 5 and 9. Sorry, add of 5 and 9, and you can see the resultant will be E, which is stored back in A. Now the next program counter location is 4, which is it's simply saying that it wants to move the value in A to 7. So here you can see that now since we are going to write to it, so so that's actually trying to fetch that instruction, and so now it sees that it's going to give the command to write to the memory location. So E will be actually pushed into memory location 7. So this is how, step by step, how instructions are executed in your processor. So whenever we have your source file, which is an assembly file, so we can use also some other include files. We use an assembler to actually translate the source file into machine code. And as I said, the machine code is usually represented as a hex file. So during this process, we can also generate a few other support files like list and map file that are useful for debugging. And if you have multiple source files, then you can also create multiple object files and so on and so forth. So here is an example of an assembly source file. So as you can see, we have some instructions that are specified like this, and then you can see there are words with a dot. So these words with dot are actually called assembly directives. They are actually not instructions, but they are assembly directives, very similar to the C directives. If I use, say, hash include, so that actually is a C directive to use such a thing. So here you can see that everything has a dot is assembly directive, and you have two instructions. So whenever you have something like this, that is actually called a label. So you're not allowed to start an instruction on column 0. So this is column 0. So you're not allowed to start any instruction in column 0, but labels and other assembly directives are allowed to start in column 0. So here are other examples, as you can see, of other terms like this. So these are all, again, reserved keywords in your assembler. So if you want to actually use a particular register, then we can actually simply use those registers. These registers are part of your special function register or your general input-output register. So these are all specific registers. So instead of actually giving the addresses for them, you can also reference it through a name which is unique. So here is an example of your flash file or your hex file. So you can see all of them are actually represented as a sequence of hexadecimal numbers, which will be programmed into your program memory. And as I said, we also can generate other type of support files for debugging. So one such file is the list file. So the list file actually lists your assembly and the corresponding machine code of those assembly instructions. So this particular file is very useful for debugging purposes. So in summary, so you have understood the components of your microcontroller, and we also seen some instruction formats of an AVR microcontroller, and also how an instruction flows in your AVR microcontroller.